Welcome everyone for today's video. In today's video, we will be looking at a very special problem concerning that what is the probability that two random integers are co-prime. So the question could be stated like follows that given we have the following series notation that is 1 by 1 square plus 1 by 2 square plus 1 by 3 square and all the way up to infinity in this manner is equals to pi square by 6, which is also called the zeta function. You might have seen in the other videos. To approach this question, we need to understand the basics of probability very well. So classical probability is used here. And moreover, a lot of manipulations are used. Nothing special would be used, but yes, creativity is utmost importance, and we will see how. Also, a general reminder that the batch we were talking about, the batch JE batch, which has begun, and I had a demo session yesterday. So actual batch begins from 23rd November 2024, and you can see some snippets of this batch. Unfortunately, my audio was not recorded, but the live class
Hello,
will be
sir. I am
uploaded. The
audible.
first live class would be uploaded on YouTube on 23rd after the
इसमें
class has been done,
एक नया वर्जन
and rest of
इन्फो
the
में
in rest of the
यस
batches, I will also try to upload snippets of those paid batches. So if you're interested to join, you can join using the link below, which you'll find in the description. You can join the WhatsApp group, and from there you can see all the payment options and all the details. And there are other members you can also connect with, who can also help you understand how the study is going on, how to get everything. So you will also get recorded lectures of every session, notes, materials, and also tests on different topics which we complete. Okay, so let us begin with this problem. So given that 1 by 1 square and all this is equals to pi square by 6, we need to find the probability that two random integers are co-prime. So what do I mean by random integers? So basically you can pick any two integers, right? You can pick 1 comma 2, you can pick 3 comma 111, you can pick anything. And there can be infinitely many choices. But then how is it even possible that we find out the probability when the sample space is infinite and so is the favorable space, right? So we need to tackle this differently. So consider this. So let me change the font here. Consider this probability that a integer is divisible by a prime p. So let's say there's a prime and we are taking it as a random prime and let the prime be called p. So the probability that any integer is divisible by this prime p is nothing but 1 by p. Okay. This is because to be divisible by the prime p, in every instance of this number basically will leave like remainders from 0, 1, 2, all the way up to p minus 1 on division by p. Correct. So these are p different remainders that any integer can leave when divided by a prime p. Correct. You can verify this. And we only want the integer to leave the remainder 0 because in only in that case is the integer actually divisible by the prime. You can take an example, take the number 11 and take the prime, let's say 17. Okay. So if 11 is divided by 17, it has no quotient, but it leaves remainders. Right now, the remainder is 11 itself. Or you can take another example. You can say 3. If 11 is divided by 3, it leaves the remainder of 2. Correct. So what happens when you divide by 3? The possible remainders are 0, 1, and 2. You see, there are three possible remainders. Similarly, by 17, there are 17 possible remainders from 0 to 16. So only in the case 0, you will say that the number is divisible by the prime p, correct? Now, probability that an integer is divisible by prime p is 1 by p. That means probability that two integers which are taken randomly and independently are divisible by a prime p would be nothing but 1 by p into 1 by p, which is 1 by p square. Okay. So two integers are simultaneously divisible by a prime p that is given by 1 by p square, the probability of that. Then probability that two integers, two randomly taken integers is what I mean, are not simultaneously divisible. So one of them can be divisible by p, but the other will not be, or both of them are not. So that's the case, which would be the complementary case to this one. This is the complementary case. Probability that two integers are not simultaneously divisible by p would be nothing but 1 minus 1 by p square, correct? And you know that every positive integer is either a prime or it is multiple of some prime or combination of a bunch of primes, correct? Now, if we want two numbers to be co-prime, that means they must have no common factors, correct? Now, if they have no common factors, that means there cannot be any prime in the whole world which can divide them simultaneously. So, for any prime p, and the probability that this prime p does not divide those random numbers that you have chosen, not simultaneously, is given by 1 minus 1 by p square. So, your required probability, let's call it capital P, is nothing but 1 minus 1 by p square, and this thing multiply it over all primes. So basically, let's say if we can list all the primes like this, p2 square, 1 minus 1 by p3 square, and so on. This infinite product of primes would be a required probability. But then again, how do we even find this? So first of all, we can write this formally like as follows: product over primes p into 1 minus 1 by p square. Okay. And now from here on, we can try and understand how to even evaluate this sum. And this is so creative. So you simply use the series that was provided to you, and you can see how the zeta function and its values are so important in so many applications of this kind of problems, in even in prime number theory. So this is your expansion, right? This is equals to pi square by 6. Okay. Okay. So let's call this zeta of 2 for now. Okay. So we can later on change this to pi square by 6. So just for the sake of notation. Okay. Now multiply this equation by 1 by 2 square. What do you get on both sides? You get 1 by 2 square, and this would be 1 by 4 square, and this would be 1 by 6 square, and there would be 1 by 8 square, and so on, correct? And this would be zeta 2 by 2 square. If this is equation 1 and if this is equation 2, what do you get if you subtract 1 from 2? So if you do 1 minus 2, you should get that this series, but all the even numbers have been subtracted, which means you should get something like this: 1 by 1 square, 1 by 3 square, 1 by 5 square, 1 by 7 square, and so on, correct? And take zeta 2 common, you get 1 minus 1 by 2 square. Give this the equation 3. Let's make this equation 3, okay? Now, 2 was a prime. Our basically our approach is that since 2 is a prime, we multiplied by 1 by 2 square and then subtracted to eliminate all numbers which had 2 in it. What is the next prime? 3. So multiply this by 3 to get 1 by 3 square, 1 by 9 square, 1 by 15 square, 1 by 21 square, and basically, since we have multiplied by 1 by 3 square, we are going to eliminate all possible numbers which have a 3 in it. So there would be no number which can now be divisible by 2 or 3 both, because we have basically eliminated both. So this should be into 1 by 3 square. Give this the equation number 4. Okay. Now subtract 3 minus 4. Subtracting 3 minus 4 should give you basically 1 by 1 square and plus 1 by 5 square. There would be no number in the denominator which has factors 2 or 3. And now we have eliminated the primes 2 and 3, correct? So 1 by 7 square, and I think a 9 is not there, 11 it would be there, and so on, correct? And when you subtract and you take zeta 2 whole into 1 minus 1 by 2 square common, you simply get 1 minus 1 by 3 square. And now do you see how is it developing to be the format we want, 1 minus 1 by p square format? So repeat this. If you were to repeat this for all primes, repeat for all primes, you can understand by the end of this process, you would end up with only the 1 by 1 square term, because every number there ever is would be combination of some prime except for 1. So in this way, when you multiply by the next prime and then subtract it and you go on forever, you will simply end up with this thing where you will get 1 by 1 square, and in zeta 2, it increases like this: 1 by 1 minus 2 square, 1 by 1 minus 3 square, 1 minus 1 by 5 square, and so on up to infinity, which means that you will simply get 1 by 1 square is equals to pi square by 6 into product over primes 1 minus 1 by p square. And therefore, we can say the infinite product of primes, which looks like this: 1 minus 1 by p square is nothing but 6 by pi square. Okay. and this is your probability P. So therefore, required probability is 6 by pi square. So there is the probability that two random integers are co-prime is nothing but 6 by pi square. So I hope you like this problem, and this is examples of creative problems. Okay, so given a series, you can find this value. Look at the manipulation that has been done here. So this is so nice. I really love this manipulations and this kind of sums, and you can also generalize it to higher powers. What is the probability that three numbers taken at random are co-primes and stuff like that? Okay. So in general, if you were to randomize it for n numbers, so basically this thing, I think the answer basically would be zeta of n. Okay. Okay, let's just say n is greater than equal to. It's like this. Okay. So I think that would be the end of this video. If you're new to the channel, please do subscribe. And if you want to join the JE batch, please see the group description. That would be there was a invite link to the group in the description. And also, if you have any doubts about this problem or anything else, please do comment and also like the video if you actually like the content. Thank you. I will see you in the next video.